we want to study conditioning, and we want to say that conditioning reduces entropy. So we compare conditional entropy versus entropy. And then we want to say that conditioned one is smaller than or equal to unconditioned one. The equality here, if and only if x and y independent. So if it is independent, basically that is entropy of x, because knowing y will not tell anything at all about x. So equality part is easy, and the inequality part is also easy, because if you move this to the other side, the right hand side becomes mutual information between x and y, and mutual information is non-negative. So that is already proved. So this is the result of the non-negativity of mutual information. So this one is true. Equality with the if and only x and y independent. So we can say that conditioning reduces entropy. And then one example is this. Basically, mutual information is equal to 0 if and only if x and y independent. So compare with this one. When you do this, basically equality, that is the equality case. Okay. All right, now let's move to the next page. Next page talks about chain rule, and we have random variables x1, x2, xn drawn from joint distribution px1, x2, xn. Then entropy of joint random variables x1 and x2 is entropy of x1 plus entropy of x2 given x1. And then if you do the three of them, then the entropy of x1 condition on x2, the rest, which is x2 and x3, and then applying one more time on this one, now to x2. So conditioning up here, right here, and then the left one is right here. So entropy of x1, x2, x3 jointly is entropy of x1, entropy of x2 given x1, plus entropy of x3 given x1 and x2. And then we can do the same with this one first. For example, entropy of x2 plus entropy of x1 given x2 plus entropy of x3 given x1 and x2, and so on. We can do it with x3 as well. And then we can continue to do that, extend it to, higher number of random variables. Entropy of a vector of random variables. And then results in previous page lead to this one. So joint entropy is smaller than or equal to sum of each one, entropy of each random variable. Basically, when we go back to previous page, conditioning reduces entropy. So this one here is smaller than or equal to entropy of x2. This one is smaller than or equal to entropy of x3. So this sum should be smaller than or equal to sum of individual entropies, which is given right here. And the equality, if and only if they are independent. Now, let's consider conditional mutual information. Conditional mutual information is the same, but here we need to take care of this conditioning in the expression. So basically, the mutual information between x and y given z is equal to entropy of x given z minus entropy of y given x and z. And this can also be written as relative entropy. Basically, relative entropy between joint distribution given z and the product distributions given z's. So that's the conditional, conditional mutual information. And then, can we say this? We can ask, let's say, mutual information between x and y given z is equal to 0 if and only if x and y independent given z. Obviously, going this way is easy because you just plug in the number, then that is a summation of log of 1, so it is 0. And the more difficult one is going this way. So mutual information is 0. Can we say this? And then the proof is exactly the same as before. So you can make use of the independence definition, and then you will get the answer, get the proof. And the chain rule for information. Let's consider this. You need to be careful here. I have a commas right here, and then I have a semicolon right here. Mutual information is between two random variables. So in this case, you need to treat the first part as a vector random variable. So this is vector random variable of x1, x2, x3. And then I want to know the mutual information between the vector and y. So this is a mutual information between this first part and the second part. So the mutual information is expectation of log of joint distribution between first and the second part, and the product distribution between the first and the second part. Then this is nothing but entropy of the first and the entropy of the first given the second, taking away this part. Okay, so entropy of the first part minus entropy of the first part given y. And then applying the chain rule of entropy, we get this. And the entropy of the chain rule, this, we get this. And then once I have written that this way, then I take a look at this first part, second part, third part together. Then, this first one is mutual information between x1 and y. The second part right here is mutual information between x2 and y given x1. This one here is mutual information between x3 and y given x1 and x2. So that's the chain rule for information.